Now that we have a more rigorous definition of an infinite series, let's revisit these geometric sums that we saw at the beginning of chapter 8.3. These terms, r to the 0, r to the 1, r squared, those form a geometric sequence. So this one on the right is a geometric series. And we know that we evaluate series as the limits of partial sums. So this tells me the partial sum of a geometric sequence. If I want to evaluate the geometric series, this is the limit of the partial sums. So in particular, if I'm only adding up the first n terms, I get 1 minus r to the n plus 1 divided by 1 minus r. Now let's think about when this limit exists. The first thing to notice is that r should not be 1. Now let's think about whether this limit exists or doesn't exist. R is some constant, it's not changing as n changes, so as long as its denominator isn't 0, the denominator gives us no problems. The numerator has this in it. So for the numerator, I'm taking the limit of a geometric sequence. And remember what limits of geometric sequences are. If my ratio is less than 1, this limit is 0. Remember, if the absolute value of r is greater than 1, this limit doesn't exist. Maybe it doesn't exist because it goes to infinity, maybe it doesn't exist for some other reason. So if the absolute value of r is less than 1, my series looks like 1 minus 0 over 1 minus r, which is to say 1 over 1 minus r. If the absolute value of r is greater than 1, this is going to not exist. So we can easily figure out this series now using our formula. 1/5 is r. My indices match. So if I add up a fifth plus 1 over 25 plus 1 over 125 and so on, this will give me 1 over 1 minus a fifth, or 5/4. In this next example, our r value is negative 10/9, and negative 10/9 is too big. The absolute value of negative 10/9 is 10/9, and 10/9 is bigger than 1. So the terms I'm adding up in terms of absolute value are getting bigger and bigger and bigger. So this one does not have a nice number it evaluates to. We say this diverges. Now let's look at what happens if we change the index where we start. This one started at 0. This starts at 2. So to understand what that looks like, let's write out the first couple of terms. This is 2/3 squared plus 2/3 cubed plus 2/3 to the 4th, and so on. There's different ways of dealing with this, but with geometric series, one nice thing is that factoring works really well. 2/3 squared shows up in all of these pieces, so I can factor it out. The first term becomes 1. The second term becomes 2/3. The third term becomes 2/3 cubed, and so on. So I can write this as 2/3 squared times the sum of 2/3 to the power I. So my index starts 0, 1, 2, and so on. Now I can use my formula, and I can see that my series is 4/9 times 1 over 1 minus r, which is 2/3. That's 4/9 times 1 over 1 minus 1/3 is 3. That's 4/3. Here's another example of a series that needs to be algebraically manipulated just a little bit before we get it into a form that's usable to us. 9 to the 2 times I is the same as 9 squared to the power I. And 10 to the I over 81 to the I is the same as 10 over 81 to the I. So in this case, r is 10 over 81, and the absolute value of r is indeed less than 1. So now we can plug this into our formula. Also, it starts at the right place. So this will look like 1 over 1 minus 10 over 81, which is 81 over 71. Here's yet another example of a series that needs some algebraic manipulation before we can plug it into our formula. We start at the right place, but our power is not matching. I'm going to rewrite this as 2/3 to the power I times 2/3 to the power 17. Now that term, 2/3 to the power 17, does not have an I in it, so I can factor it out of my sum. Again, this is the type of algebraic manipulation we talked about when we were doing Riemann sums. So the terms that are left are 2/3 to the I. Now I can use my formula. My indices are right. My r is 2/3. So this looks like 2/3 to the power 17 times 1 over 1 minus 2/3. That's 2/3 to the power 17 times 3. Or if you like, 2 to the power 17 divided by 3 to the power 16. Let's see an example now that combines a few different algebraic manipulations. This example doesn't start at the right place. It doesn't have one number r raised to the power I. This I index is off by 1, and this I index is multiplied by 2. Piece by piece, I need to turn this into something that looks like my original formula. On the top here, this is the formula that I want to use. The bottom, this is what I need to evaluate. So step by step, we need to make this look more and more like the formula above. And we've seen all of these pieces before. So this I plus 1, I can handle that by rewriting the numerator as 3 to the power I times 3 to the 1. This 2 to the 2I can handle that by writing this as 2 squared, which is 4 to the power I. So this is 3 times 3/4 to the power I. Since 3 doesn't have any i's in it, I can factor that out. Now the only problem I have left is the index. I've got r to the power I, r is 3/4. The absolute value of r is less than 1, so it will converge to some number. I just need to manipulate this starting point. Again, a nice way of doing that is writing out these terms and then figuring out what's going to factor. So this is 3/4 to the power 10 plus 3/4 to the power 11 plus 3/4 to the power 12, and so on. So what I can factor out is 3/4 to the power 10. I can factor out that first term, and this works well with geometric series, doesn't work so well with non-geometric series. My first term is now left as a 1. My second term is now 3/4. My third term is 3/4 squared, and so on. Now I can write that again in sigma notation. This is the sum of 3/4 to the power I, and now I starts at 0. This is 3/4 to the 0, 3/4 to the 1, 3/4 to the 2, and so on. Now, at long last, my indices are correct. My r is 3/4. My powers work correctly. Now I can just plug this into my formula. So this is 3 to the power 11 divided by 4 to the power 10 times 1 over 1 minus r. R is 3/4. That's 3 to the power 11 divided by 4 to the power 10. 1 minus 3/4 is 1/4, so this is 4. So 3 to the power 11 divided by 4 to the power 9. Let's think about some more examples. This is what you could call a partial sum. It's a finite series. Rather than add up 100 things, I can use this partial sum formula up here. In this example, r is a fifth, n is 100, so my power is 101. Here's a slightly different example. I have a finite number of terms, so it's a finite series, not an infinite series, but they don't start at 0, so I can't jump right into here. One way to evaluate this, well, there's only 3 terms, so I can just add them up. This is negative 10 ninths to the power 100 plus negative 10 ninths to the power 101 plus negative 10 ninths to the power 102. That's one way of doing it. I want to think about a different way of evaluating this. For this particular one, it's probably harder, but if you had a bigger gap between, if you had to add more terms, here we only had to add 3, but if you had to add more, this other way might be easier. I'm going to write this as the sum, I goes from 0 to 102 of my terms, minus the sum, I goes from 0 to 99. Of my terms. So first let's think about why that even works. The blue sum is a0 plus a1 plus a2 all the way up to 102. The red term is, we still start at 0, but we end at 99. So if I were to subtract these, I would just cancel off all the terms I'm not interested in, and I would get my 100th term, my 101st term, and my 102nd term, which is exactly what I want. So that's why I'm allowed to write this sum as the difference of these two sums, and the reason I might want to do that is that both of these can be now evaluated using our formula. The blue one is 1 minus my ratio, negative 10 ninths, to the power n plus 1, so that's 103, divided by 1 minus my ratio, negative 10 ninths. The one on the right is 1 minus my ratio, negative 10 ninths, to the power n plus 1, which is 100, divided by 1 minus my ratio. So that's another way to evaluate this series, this sum, and this answer that we found needs to be the same as this sum here. Just take some algebra to make them look like one another. Here's another example that doesn't immediately fit our formula. Instead of starting at 0, I start at negative infinity. So whenever you're really not sure what something looks like, it can be really helpful to write out the first couple of terms. In this case, I'm going to go backwards. There's a 5/3 to the 0. The term before that is 5/3 to the negative 1. And the term before that is 5/3 to the negative 2. And the term before that is 5/3 to the negative 3, and so on. Now I'm going to rewrite this. This is the same as 3/5 to the 0, because anything to the 0 is 1. This is the same as 3/5 to the 1. This is the same as 3/5 squared. This is the same as 3/5 cubed, and so on. So I can see that I can rewrite this as the sum going from 0 to infinity of 3/5 to the power I, and now I can immediately plug that into my formula. 3/5 absolute value is less than 1, so this converges, and we get 1 over 1 minus 3/5, or 5/2.